So guys, in this lecture we will see differential relay. So as the name suggests differential means we are in need of two or more similar electrical quantities whose difference should be there. If there is a difference and if it exceeds a predefined value, the relay will operate. So this is the simplest differential relay. In this case we use two CTs which are identical. That means both the CT will have same turn ratio and identical in construction. So the equipment to be protected is put over there in between these two cities, primaries of these two cities. This dotted line will show this dot line will show where is the equipment to be protected, whether it should be a alternator or it should be a transformer. Fine, this is the operating coil of the relay. And what is our need? Our need is the current through this operating coil should be zero whenever there is a fault outside this protective zone. In between these two CTs, the zone is known as the protective zone. And if the fault, in this case, this is the fault occurs outside this protecting zone. So this fault is known as through fault. If the fault occurs outside the protecting zone, that means that fault is known as through fault condition. Fine. So what the relay will do in this case? The relay will have to be insensitive. That means the relay should not operate under this condition. So we are clearly seeing that if the CTs are identical, the secondary current of both the CT will be also same. Therefore, the resultant current in the operating coil should be zero. Now consider this case. In this case, the fault occurs between the protecting zone. Now in these two figures, figure A and figure B, in this case we are seeing that the system is fed from one end, that means input is from this side, and in this case the system is fed from both the end. This is the first input and this is second input. So in this case what happens, we see clearly that if there is a fault in the protecting zone, there is a relative current, there is an appreciable current through the operating coil and the relay will operate. Similarly in this case, if there is a fault over there and this is the current, this is the I1 plus I2 is resulting current through the operating coil and the relay will operate. So this type of protection is known as Moore's price protection. Okay, fine, this type of protection is known as Moore's price protection. Now this is the case when the CTs are identical 100% identical, but in practice or in practical case these CTs will vary. These CTs will vary because of their magnetic properties, and there is a difference of current in their secondaries, and due to this difference there is a resultant current in the operating coil and there is a malfunction of the relay. So in order to accommodate this or in order to rectify this mal-operation of differential relay, what we are doing, we are putting another coil. You can see in this figure, this is a coil. This coil is known as restraining coil, and we will put this operating coil in the middle of this restraining coil so as to avoid the malfunction of the relay. So how it works, let us see. Now in this case, this is the current through the operating coil. If there is a difference in the CTs, there is a resultant current in the operating coil which is I1 minus I2. Okay, so the torque developed in this operating coil is proportional to the MMF produced in this operating coil. Now let if N0 be the number of turns in the operating coil, so the torque produced in the operating coil is proportional to the MMF in this coil, that is I1 minus I2 into N0. And what is the torque in the restraining coil? So the torque in the restraining coil is proportional to I1 plus I2 into NR by 2, where NR is the number of turns in the restraining coil. So how this figure comes, and I1 plus I2 into NR by 2. Now look over here. Now if NR is the total number of turns in the restraining coil, then I1 current will flow through N by 2 turns, while I2 current is flow in another remaining N by 2. This is the case. I1 current is flowing in N by 2 turns and I2 current is flowing in this N by 2 turns. So the effective number of turns, if we add both this MMF of turn 1 and turn 2, so we will get the effective number of turns, that is I1 n by 2 plus I2 n by 2, and the resultant will be n into I1 plus I2 by 2. This n in our case is NR. So the torque is proportional to I1 plus I2 into NR by 2. So under balance condition, under standstill condition, both the torque developed in the coils will be equal. That is I1 minus I2 into N0 is equals to I1 plus I2 into NR by 2. So this is the resultant expression we have obtained of the functioning of the relay. That is I1 minus I2 upon I1 plus I2 by 2 is equals to the ratio of the number of turns in the restraining coil and upon number of turns in the operating coil. So this is the operating characteristic of my differential relay. It clearly shows that under normal and through fault condition. So again, through fault is the fault when the fault is occurring outside the protecting zone. Under through fault condition, the biased force produced by the restraining coil is greater than this is the biased force which is produced by the restraining coil. This is greater than the operating force produced by the operating coil. So the relay will not operate. But under internal fault, when the fault occurs within the protecting zone, the operating force becomes more than the biased force. Remember, what is biased force? The force generated by the restraining coil. So the relay will operate. And it is clear that from the characteristic of the differential relay, that for the low current, except the low current, the characteristic is a straight line. So okay, for further queries you can contact me.